Here is one last problem of solving a rational inequality. It's similar to the last one with one extra step in the beginning, but I thought it might help you to see maybe one more example of how these work, and then you should try them on your own in the practice sheets and in the homework. All right, so this problem is only different because in the beginning, it is not in factored form, right? So remember the first step for analyzing any rational function would be to factor it if we can. So we're going to try to factor the top and the bottom. So in the top, I have x and then I need something that multiplies to be 12 but adds to be 7. So I'm thinking 3 and 4. Because I want positive 12, but I could add negative 3 plus negative 4 to get negative 7 when I add. Okay? And then on the bottom, x squared minus 4 is a difference of two squares. It's x plus 2 times x minus 2. Okay? So you notice with this function that nothing divides out. So if you recall from the rational function chapter or section, then negative 2 and 2 would be undefined in the function, and they would both be vertical asymptotes, right? Because they do not divide out. All right, so where is f of x equal to 0? Well, that is the x-intercepts, right? So x is equal, or f of x is equal to 0 at x is equal to where the 0 is in the numerator. I almost wrote numerator. Maybe it should be called a numerator. All right, the numerator. There we go. So the zeros of the numerator are 3 and 4. Okay. So that's the answer to part A. But remember, for our sign chart, we also need where the function is undefined. And that is what is the zeros of the denominator. Okay, so the zeros of the denominator are x is equal to negative 2 and positive 2. All right, so let's create our sign chart. Throw it over here this time. So we've got a negative 2 as the lowest number. Then we have 2, 3, and 4. Notice you definitely don't need to draw it to scale. Doesn't matter. Now we have to put test points in between each of these. So there's a lot of test points there. So we need a negative 3. Between negative 2 and 2, I would always put in 0 there. Here you're going to have to put in 2.5. And here you're going to have to put in like 3.5. And here you could put in, say, 5. Okay? So all the test points, negative 3. Now, I definitely prefer to put them into the factored form of the equation. I know you have the other form. I guess if you're using a calculator heavily, you could just type it all in with that number in, but I think it's easier in factored form kind of by hand. So that's negative 3 minus 3 times negative 3 minus 4 divided by negative 3 plus 2 and negative 3 minus 2. Remember, I'm just putting in negative 3 for x. Okay, so I need to know whether it's positive or negative. So that's a negative number there. That's a negative number. This is also a negative number, and this is a negative number. Okay, so four negative signs is an even number. So this part is positive. Okay, anytime you have an even number of negative signs. All right, we're going to put in 0 to the function. So that's 0 minus 3 times 0 minus 4 over 0 plus 2 times 0 minus 2. Okay, so the top is a negative and then a negative, and the bottom is a positive and then a negative. Okay, count up those negative signs. There are 3. That means that it will be a negative because it's an odd number. So that is this section of the graph or the function is negative. Let's put in 2.5. Ooh, super fun. Okay, 2.5 minus 3 times 2.5 minus 4 over 2.5 plus 2, 2.5 minus 2. Okay, top is a negative, bottom is a positive, and then a negative. No, sorry, a positive, right? 2.5 minus 2, positive. So that is 2 negative signs, two negative signs would be an even number, so that is positive. All right, put in 3.5. You get 3.5 minus 3. 3.5 minus 4. 3.5 plus 2, and 3.5 minus 2. All right, so 3.5 minus 3 is actually positive, but then this next one is negative, and then these are both positive. So with one negative sign, that means that this area is negative. Finally, I'm going to put in 5. So I'm thinking that's going to be all positives. I'll write it out, but 5 minus 3, this is how you show your work anyway, so you kind of have to write this stuff down. So 5 minus 3 over times 5 minus 4, 5 plus 2, and 5 minus 2. That is a positive, positive over a positive, positive. So this area of the graph is positive. Cool. Okay. So now I'm going to answer where is f of x less than 0. So remember, that's just where it's negative. Oh, before I do that, right, for rational functions, hint, right, helpful hint, another helpful hint is the zeros are 3 and 4, so put like dots, solid dots on those so they can be used. And then the undefineds put open circles so you never use those. Okay, that's how you get these problems right? All the little details right. So where is it negative? It is negative from negative 2 to 2. And union with, looks like 3 to 4. Remember, my other helpful hint is only answer the zeros and the undefineds. Do not answer the test points. That's why I put them up here in a different color, so I would not use them. I only want to use these 4 numbers in the bottom of the graph as my answers. Okay, now for part D, if this is the negatives and the zeros, okay, then I want to say negative 2 to 2 doesn't change because those are undefined, so they're not negative, they're not 0, anything, okay? So that's negative 2 to 2 parentheses. Then I still need 3 to 4 is negative, but I want to bracket 3 and 4 because those are equal to 0. Okay. Now where is f of x greater than 0? That's the positives. So that looks like, I'm kind of running out of room. Positives. Okay. It starts over here, negative infinity to negative 2. And then another positive is from 2 to 3. And then the final one is 4 to infinity, all parentheses. Okay, and then finally, if we want to include the positives and the zeros, okay, then we're going to go negative infinity to negative 2, parenthesis 2 to bracket 3, and bracket 4 to infinity parenthesis. Okay, so I'm just making brackets out of the ones that are zeros. I hope that that helps you define what do you do with the undefineds versus what do you do with the zeros. And that's really the only difference between the rational inequalities and the polynomial inequalities.